Hello and good morning, everyone. I'm Mohammad Mahdi Asghari, and today I'll present our research on integrating solar photovoltaic systems with battery storage for electric vehicle charging infrastructure. This is a joint work between Shad-based University, Alti University, and King Mongkut University of Technology, North Bangkok. The structure of the presentation is organized as follows. After a brief introduction of the concept, the methodology of the study will be expressed in the second section. Then the implementation results of proposed method will be described. Finally, the conclusion and recommendations of the current work will be presented in the last section. This brings us to our research objective. Can we effectively integrate solar photovoltaic systems with battery storage to create sustainable, grid-independent EV charging infrastructure? Specifically, we wanted to quantify how much charging demand can be met through local renewable generation in a real-world urban setting, and understand the seasonal performance variations in Central European climates, specifically in the city of Munich. We designed a grid-connected solar charging station for Munich, Germany. The system consists of three main components: a 45.2 kilowatt peak photovoltaic array tilted at 48.1 degrees to match Munich's latitude, a 300 kilowatt hour lithium-ion battery storage system, and three charging ports serving a daily demand of approximately 228 kilowatt hours. Munich was chosen as a representative Central European location with pronounced seasonal solar variation. We used Transys software to simulate the system's annual performance with a 50-minute time resolution. The simulation incorporates real meteorological data from PBGIS and Meteor, and realistic charging demand profiles from the ELAD-NL database. Our energy management strategy prioritizes direct PV2 load supply first, then charges the battery with NS surplus, exports excess to the grid, and imports from the grid when local generation is insufficient. The photovoltaic system uses 78 models of 580 watts each, totaling 45.2 kilowatts. Based on Munich's solar yield of 950 kilowatt hours per kilowatt peak annually, this provides about half of the theoretical full solar coverage. A deliberate design compromise balancing renewable contribution with economic feasibility. The 300 kilowatt hour battery was sized to provide one full day of autonomous operation at 80% depth of discharge, addressing the temporal mismatch between daytime solar generation and predominantly evening charging demand. This slide outlines the methodology used to generate the charging demand profiles. On the left, you see the yearly load profile with a 50-minute resolution. This dataset represents the power demand in kilowatts across an entire year, giving us a high view of charging behavior over time. Notice the variability in the load, including intermittent peaks, which reflect periods of high charging activity. The data used for this analysis comes from ELAD-NL, which provides real-world charging session data. Using this dataset allows us to base our simulations on realistic usage patterns rather than synthetic assumptions. By modeling the load at this resolution, we capture both daily fluctuations and extreme demand events, which are critical for accurately assessing system performance and infrastructure requirements. This load profile serves as the primary input for the simulations and analysis as presented in the following section. Annual average tell us the system works, but they don't tell us how it works under different conditions. We selected the first week of January and July as representative periods for detailed analysis, along with an entire year for a macro performance analysis. January representing the worst-case low radiant season after winter solstice, and July representing peak summer solar conditions. Look at the load profiles on the right. They're nearly identical between seasons, both averaging around 220 kilowatt hours per day. This is key. By keeping demand constant, while solar availability varies dramatically, we can directly measure how seasonal irradiance affects system performance. The charging behavior doesn't change with seasons, but the solar resource changes by a factor of 3. And that's exactly what we want to analyze. Now let's look at the results. The photovoltaic system generated 55.42 megawatt hours annually against a total charging demand of 82.92 megawatt hours, achieving a solar fraction of 66.84%. This means approximately two-thirds of the charging energy comes from local renewable generation. The graph shows pronounced seasonal variation in PV output, with substantially higher generation during summer months. The seasonal difference is dramatic. In the representative July week, average daily PV output reached 188 kilowatt hours with battery state of charge exceeding 90%. In contrast, the January week showed only 68 kilowatt hours average daily output, with battery state of charge constrained below 65%. This threefold difference in generation between summer and winter is the fundamental challenge for year-round operation in Central European climates. Despite the high solar fraction, the system remained a net grid importer throughout the year. We imported 115.37 megawatt hours while exporting 91.81 megawatt hours, resulting in a net grid dependency of 23.56 megawatt hours annually. The weekly comparison shows that during summer, imports and exports are nearly balanced, while winter requires substantial grid support. The sharp import spikes correspond to fast charging events when multiple ports operate simultaneously. This table summarizes our key findings across 3 time periods. The annual solar fraction of 66.84% demonstrates that medium-sized PV battery systems can significantly reduce grid dependency. However, the seasonal asymmetry is clear. Summer operation approaches energy balance with comparable import and export, while winter shows 1,180 kilowatt hour net deficit in just 1 week. This confirms that complete energy autonomy remains challenging without substantially oversizing the system. Our main conclusions are threefold. First, PV battery systems can significantly reduce the carbon intensity of urban EV charging. We achieved nearly 67% renewable contribution. Second, seasonal solar variability in Central Europe creates a fundamental asymmetry. Summer self-sufficiency versus winter grid dependence. Third, while complete energy autonomy is theoretically possible, it would require massive oversizing of both PV and storage, making it economically impractical. The grid-connected hybrid approach represents the optimal balance. For future work, we're investigating 4 areas. Optimized charging strategies using demand response AI-based energy management systems that can take advantage of dynamic electricity pricing in European markets. Economic feasibility analysis of larger storage capacities and vehicle-to-grid integration. Before closing, I'd like to acknowledge funding from National Science Research and Innovation Fund of Thailand, Shaikbesh University, and our collaborative partnership through the Electrical Engineering Thai French Research Center. Thank you for your attention. I'm happy to take any questions.